please jot down that title. And let's start by, I apologize for yesterday's notes. I mean, they weren't that great. Let's start by just writing down what a radical function looks like. You don't even have to write radical function. This is all that matters, that you understand that y equals a square root of x minus h plus k on the outside at the end. This is very similar to vertex form equations where we had y equals a parentheses, these used to be parentheses, with the square on the outside plus k. Same exact thing, and it tells us the same exact thing. Back when we did parabolas, the hk value, that was the most important point. It was the vertex. Right here, if you do the coordinate hk, it's also the most important point of a square root function. It's the beginning point of where your curve begins. It starts off at the point hk and it shoots off in a curve direction. Anyway, let's start by writing down y equals a squared of x minus h plus k. And then let's write down the steps. How do we graph this? I did give you some steps yesterday. Here's some, I guess, revised steps to make it a little more easier to understand. Step 1, box in the function, leave out h and k. So you box the y equals a squared of x, leave out the h and k. Step 2, graph the box function. That means no h and k. Graph this guy right here. And how do you graph this guy? You plug in your xy table, you plug in nice numbers that you'll be able to do the square root of. So like 0 would work, square root of 0 is 0, and then multiply by whatever numbers out here. So that'll be your input and your output. Plug in 1 because the square root of 1 is 1, and then multiply it by whatever a values out here. Do the square root of 4, plug in 4, that way you'll get 2, and then multiply a times 2, and so on and so on. So you get coordinates for this boxed function, and then your final step would be to shift those coordinates according to your h and k. And you always think opposite on h and you take k for what it is. So let's go to our worksheet of graphing square root functions. I think we left off on this one right here. But even before doing this one at the bottom right corner of our front page on that worksheet, let's go back up to this one to demonstrate the process of the steps that you guys just copied down. So you want to begin by boxing in, ignoring h and k. You box in this function, and this is technically your parent graph function, and you make an input-output table, plug in nice numbers that you could do the square root of. Like the square root of 0 is 0. The square root of 1 is 1. The square root of 4, when you plug in 4, is 2. The square root of 9 is 3. So you get these coordinates, which are your parent graph coordinates, and I actually graphed them over here in blue, 0, 0, 1, 1, 4, 2, and 9, 3. Those are the blue dots. And then once you have graphed the parent graph coordinates, then you shift these coordinates according to h and k. H is always inside parentheses, in this case inside the square root, with x, and you think opposite of what you see here. So you have a plus, which means that your h is really equal to negative 2. Now that means that you're going to shift it 2 units to the left. And the k value out here, you take it for what it is, which is negative 3. And that means that you're going to be shifting 3 units down. So you take all these blue coordinates and go 2 to the left and 3 down, and you get to your new coordinate. 2 to the left and 3 down, get to your new coordinate. 2 to the left, 3 down. 2 to the left, 3 down. So you get to this new graph. This graph has the most important point, the beginning point, which is your hk. And what is our hk coordinate here? It's obviously negative 2, negative 3. H, negative 2, k, negative 3. That means that this beginning point is at negative 2, negative 3, which it is. Now that beginning point will help you determine the domain and the range, because your domain are your x values either to the left or to the right of that beginning x value negative 2. So this beginning point is at the x value of negative 2, and it doesn't exist at negative 3 or at negative 4 or at negative 5. It exists at negative 2 and also at negative 1 and 0 and 1, 2. It exists at negative 2 and to the right. That's why we have domain being x is greater than or equal to negative 2. The beginning point is negative 2, negative 3. So when you're talking about the range, where's the range at? It's the y values. And what's the y value of your beginning point? It's negative 3. So right here, your y value is negative 3, and it's all above, not below. So at negative 3 or above, that's y is greater than or equal to negative 3. Do we understand that? You're going to have to do this on the quiz, right? 2 questions will be to graph the radical function and then also state the domain and the range. You're getting a point for each of those. Okay, so we've gone through the steps. This one down here, this one on the bottom right corner, it's really not a good one to follow the steps because it doesn't even have an H and K. But the reason why I'm doing this one is to demonstrate vertical stretches and compressions. Do you guys remember parabolas? When the A value was greater than 1, the parabola got vertically stretched. Or when the A value was less than 1, closer to 0, it got vertically compressed, it got wider. I hope you guys remember that. Same thing is going to happen here with this A value, okay? And to really demonstrate what happens from the original parent graph to these new 2 graphs, let's actually graph the parent graph, y equals the square root of x. And if we graph y equals the square root of x, doing inputs and outputs, let's plug in 0, we get the square root of 0, which is 0. Plug in 1, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. And those are all the coordinates of your parent graph. 0, 0, 1, 1, 1, 2, 3, 4, 2, and 9, 3. So those are the dots of the parent graph. I could draw it if I wanted to, but let's see what happens when the A value of 1, right, the A value is 1 right here, becomes the A value of 2. All right, so let's actually come up with XY table inputs and outputs for this red one that I just boxed in. So again, you're going to use the same perfect square values to plug in. For example, 0 always works great. When you plug in 0, the square root of 0 is 0, and when you multiply it by 2, it's still going to be 0. Another good one would be 1, because you could always do the square root of 1. The square root of 1 is 1, and when you multiply it by 2, you will get 2. Let's also plug in a nice perfect square number 4. When you plug in that 4 right there, the square root of 4 is 2, but then when you multiply it by 2, it takes you back to 4. Now let's plug in the next perfect square number, which is what? 9. And when you do the square root of 9, you get 3, but when you multiply it by the A value of 2, what do you get? 6. So check out these coordinates. It still has the same beginning value 0, 0. That's because the HK coordinate is 0, 0. But instead of the coordinate 1, 1, you now have the coordinate 1, 2. Instead of the coordinate 4, 2, you have 4, 4. Instead of the coordinate 9, 3, you have 9, 6. So what is it that happened comparing the blue dots to the new red dots? This is what we call a vertical stretch. See, the distance from the x-axis to this blue dot, that's the parent graph, gets vertically stretched. It gets further away from the x-axis. What do you guys think? Okay, so obviously the A value that's 2, it got stretched. It got stretched. It got stretched. It's called a vertical stretch. If it would have been 3, it would have been stretched even further. If it would have been 4, it would have been stretched even further. So, like, let's say you had 5, it would look like a curve, something like this, right? Okay, so that's a vertical stretch. What's going to happen if I were to do this one and get the coordinates of that one? That would compress. Why? Because the A values are less than 1, greater than 0, but less than 1, which is a compression. The closer it gets to 0, the more flattened out it gets, all right? So if I were to do a XY table for that green one, the square root of 0 is 0. Multiply it by half, it's still 0. And then the next one, the square root of 1 is 1, and then times 1/2, that will be 1/2. And then the square root of 4 is 2, and 2 times half is 1. And the next perfect square number 9, the square root of 9 is 3, and 3 times half, what's half of 3? 1.5. So we still have the same beginning point 0, 0, because the HK is still 0, 0. But instead of going 1 over 1 up, we have 1 over halfway up. And the next coordinate would be 4, 1. And the last coordinate would be 9 and 1.5. So again, the blue one that starts at 0, 0, that's your parent graph. That's the one that has the A value of 1. What happens when I change it to the A value of 2? That's what we call a vertical stretch. Same beginning point, but it's getting vertically stretched. And what happens when your A value is less than 1, it's what we call a vertical compression. Same beginning point, but it's a vertical compression. It gets, the parent graph got compressed, it got smashed, so it's a little bit narrower, right? Closer to the x-axis. So that's just to demonstrate vertical stretches and compressions. That's to demonstrate how the different A values will affect the curve itself. And I don't even know if we're going to, well, I guess we might need this for tomorrow's quiz, but more importantly later on in the future when we describe transformations. Anyways, let's flip this over to the other side. So let's do a couple of these. Pick one. 2, 3, 4, 5, 6. How about we do 6? 6 is interesting. And if we follow the steps, where the heck are the steps? Okay, so here are the steps. If we follow those steps, let's first box in the y equals a squared of x. So let's do that with number 6. Let's box in y equals a squared of x. We're ignoring h and k. And let's come up with a xy table for that boxed in function ignoring h and k. So because we're dealing with a square root, let's do nice perfect square values as the inputs. So a nice number that you could plug in would be 0. And think about that. The square root of 0 is 0 with the negative in front. It's negative 0, which is still going to be 0. When we plug in a 1 right here, the square root of 1 is 1, but with the negative in front, what'll that be? Negative 1. Next perfect square number I could plug in would be 4. Plug in 4. The square root of 4 is 2 with the negative in front. That'll be a negative 2. And last but not least, let's plug in a 9. And when I plug in a 9 right here, the square root of 9 is 3, but with the negative in front, it's a negative 3. So if we graph these coordinates, 0, 0, 1, negative 1, 4, negative 2, and 9, negative 3, you end up with those points. But that's not your final graph. You see, your final graph needs to take these coordinates and shift them according to h and k. What is your h and what is your k?
-3 and 3.
Negative 3 and positive 3. You always think opposite of what you see here. So the h value is negative 3. That really means that you're going to be shifting your coordinates 3 units to the left, and k being positive 3, it's 3 units up. Okay? So we're going to have to shift 3 units to the left and 3 units up. So you're going to take each one of these coordinates and move 3 to the left, 1, 2, 3, and 3 up. 1, 2, 3. So you'd put your new dot right there. And that's technically your beginning point, right? Your beginning point is the coordinate hk, which would be negative 3, 3. Okay, so that's your beginning point, negative 3, 3. If you take every single coordinate, move it 1, 2, 3 over, 1, 2, 3 up, you'll end up at that point, and so on and so on. So if I take this one, 1, 2, 3, 1, 2, 3, I'm there. The last one, 1, 2, 3, 1, 2, 3, right there. And there's my graph. So the blue dots was my original y equals a squared of x. The red dots are my actual final graph that I really do want to represent. If you accidentally drew this blue one, just put 2 x's on it so I know that this is not the one that we're talking about. This is the one we're talking about right here, the red one. Okay, so now that we know the beginning coordinate is negative 3, 3, we could use that beginning coordinate to identify the domain and the range. So the domain would be your x values. So the x values, this graph, it has the beginning x value of negative 3. So think about that. The number line, the x number line, negative 3 is right here. That's where it begins at the x value of negative 3. Now, is it to the left of negative 3 or to the right of negative 3? Anybody awake? It's to the right, which means what? X is greater than or equal to that x value of negative 3, that beginning x value of negative 3. How about the range? The range are your y values. So what's your beginning y value here? It's 3, right? It's at the y level of 3. And is it above 3 or at 3 or below? At 3 or below, right? So how do we describe at 3 or below? We're going to say y is what? Less than or equal to 3. So there's your domain and range. So on tomorrow's quiz, you're going to get a couple points for graphing it correctly. You're going to get another couple of points for stating your correct domain and your range. I like to graph the original coordinates, ignoring the h and the k, and then shifting them according to h and k. If you don't like this like visual shifting of 3 over and 3 up, you could do it numerically with these coordinates. Like, what does a shift of 3 to the left actually mean? It means that you're going to go to each of your x values and subtract 3 from it. You would technically, numerically, have to subtract 3 from here, subtract 3 from there, subtract 3 from there, subtract 3 from there, and you get your new x values. And your k value of up 3, that means that you'd be adding 3 to all these y values, thus giving you your new xy coordinates. But I think it's easier to just graph the original ones and then shift them 3 to the left and 3 up, and you'll have your new graph. Okay? So, are there any other ones? Well, actually, let's do this. Let me pause it. So we have all the answers here. I'm just going to scroll through them on the video. That way you could check your work at home. Just hit pause on the video. There's the answer to 3 with the appropriate domain and range. Obviously, you can't copy it right now, but let's go to 4. With the appropriate domain and range over here. Let's go to 5. So again, I want you to do this on your own. Watch the video, hit pause so you could check your answer, see if you did it right. And 6, we just did. And again, if you happen to accidentally draw the original one, just put 2 X's on it so I know that that's not the one. So please finish this, check your answers on this video, and also review your previous quiz. So here's our previous quiz. It's going to be almost identical to it, right? Same exact stuff. I will ask you to add. This is just the notation for adding the 2x plus 1 with the x minus 3. This is just the notation for subtracting 2x plus 1 minus the x minus 3. And of course, you need parentheses so you could distribute the minus sign. I do want to go over number 4 particularly. A lot of people messed up on number 4, and it's really ridiculously easy. What does 4 say? That notation says to take your f function and divide it by your g function. So your f function is 2x plus 1, if you write that. So far so good. Divided by your g function, which is x minus 3. And that's your answer. You don't have to do anything. But whenever you have a fraction with a variable in the denominator, you should state what x cannot be, and it cannot be a positive 3 in this case. Why? Because if it were a 3, 3 take away 3 is 0, and that would make this whole thing undefined, and we don't want an undefined fraction. So you needed both parts to get full credit. We will have where we plug one function into the other function, right? And right here, when you plug in a function into another function, you will end up with a variable expression. But there's also going to be some where you plug in the number -2 into the g, get an answer, plug in that answer into the f, and you're going to get a numeric answer, not a variable expression. Would anybody like to see any of those?
15.
15? Oh, jump into 15. Okay, so 14 and 15 were interesting, and you should know how to find the inverse of a function. How do you find the inverse of a function? You rewrite it, but you switch x and y and then solve for y. So instead of y equals 3x minus 2, we're going to put x equals 3y minus 2. And we now need to solve for y. Okay? So let's solve for y. Plus 2 plus 2. You're going to have x plus 2 equals 3y. Final step would be to divide by 3, and there's your inverse function. You could put y with the little -1 exponent, which is the inverse notation. And that's your answer for the inverse, with the answer for number 14. You could have also split that denominator, and you could have put it as 1/3 x plus 2/3. Either one's perfectly fine. You're going to have to do this on tomorrow's quiz where I give you a function, you switch x and y, and you solve for y. In addition to that, I wanted you to graph this and its inverse. So we should all remember from Algebra 1 to graph y equals mx plus b, it crosses at -2, and you will go up 3 over 1. The slope, the m value is up 3 over 1. So if you go up 1, 2, 3 over 1, you'll end up at the coordinate 1, 1. And you could continue to go up 1, 2, 3 over 1. You could even use that pattern backwards to extend it this way. Now each one of these red dots is a coordinate. And this is the line of y equals 3x minus 2. They want you to graph its inverse also. Now this right here is its inverse. But that'd be kind of funky to graph y equals 1/3 x plus 2/3. Because that y-intercept would cross right here at 2/3, right? And you'd have to go up 1 to the other 2/3 over 3. So it's easier to just take these coordinates, this coordinate right here, that's actually 2, 4. This coordinate right here, that's actually 1, 1. This coordinate down here, which is 0, -2. And this coordinate over here, which is -1, -5. And just switch all those x and y values. And the 2, 4 will become 4, 2. 1, 2, 3, 4, up 2. So here's your new inverse coordinate of 2, 4. It's 4, 2. What's the inverse coordinate of 1, 1? Switch 1 and 1, and it'll still be 1, 1. So here you would have the line so far. What's the inverse coordinate of 0, -2? It'd be -2, 0, which would be right here. So there's your line, your inverse line. Here's your original, here's your inverse. It really truly is a reflection over the y equals x line. Any other questions? On 16, 17, 18, or 19, I'm not going to do the work, but I want to just describe again what you need to do. In order to check whether they're inverse functions or not, you need to take the f of x function and plug the g of x right into it. And if it works out to equal x, then so far it is an inverse function, but you have to do both ways. You also have to take your g of x function and plug the f of x right in it. And that should also equal x. So if this equals x and this equals x, then yes, they are inverse functions. If you do the first one and it doesn't equal x, if it's 2x or x minus 3, then you could just stop what you're doing and say, no, f of x and g of x are not inverse functions. I don't know. I guess that's about it, right? We should be able to start out this semester with an A. Good luck.